Every day, we interact with all kinds of information like letters, numbers, emojis, photos, videos, and even AI generated text in today's world. To us, they're all completely different. But inside a computer, none of these exist the way we see them. At its core, a computer relies on just two symbols, 0 and 1. So here's the question. Out of everything it could have used, why did computers choose only 0 and 1? Computers don't actually understand numbers the way we do. When you type the number 5, it feels like the computer knows exactly what it means. But in reality, 5 is just another symbol from our perspective. Inside the computer, the symbol has no meaning by itself. A computer can't recognize numbers, letters, or words the way humans can. Instead, it only detects the physical state of its electronic circuits. It's simply checking one thing. Is electricity flowing or is it not? And that simple idea is the reason computers are built around just two states, on and off. This naturally leads into the next slide about electricity having two reliable states. Now that we know computers detect physical states, the next question is, what physical states can they actually detect? The answer is electricity. As you can see, electricity has only two reliable states. Either current flows or it doesn't flow. When current flows, the computer treats it as on. When there's no current, it treats it as off. These two simple electrical states are stable, easy to detect, and extremely reliable. And that's exactly why computers represent information using just zeros and ones. But how do computers control this flow of electricity? That's where the transistor comes in. So, we know electricity can either flow or not flow. But how does a computer control that flow? The answer is a tiny electronic component called a transistor. Think of a transistor as an incredibly fast electronic switch. When it allows electricity to pass through, the state is on, where we represent it as 1. When it blocks the flow of electricity, the state is off, which we represent using 0. On its own, a single transistor isn't very useful. But when billions of these switches work together, they form the foundation of every modern computer. A single transistor can only do one very simple job. As you can see, one tiny switch can't play music, it cannot open your browser, and it cannot definitely run your favorite games, right? The real power comes when billions of transistors working together. These billions of tiny switches are packed inside your CPU or processor. Working together, they perform billions of operations every second, and that's what allows your computer to run operating systems, open applications, play videos, and do whatever you do using it. But simply having billions of switches isn't enough. They also need a way to work together and make decisions. So far, we have seen that a transistor can be only on or off. But how do billions of these switches actually solve problems? They do it by working together to form logic gates. Take the AND gate as an example. As you can see, it produces an output of 1 when both the inputs are 1. If either input is 0, the output says 0. A simple way to think about this is a door with two keys. The door only opens when both keys are turned on. In exactly the same way, an AND gate only turns on when both the inputs are on. By combining millions and billions of these logic gates, computers can make decisions, perform calculations, and execute the programs we use every day. Now, if it's an OR gate, either of them should be 1 and the result will be 1. Everything we've talked about so far leads to one powerful idea. No matter what you're using on your computer, it all has to be represented in binary, whether it's a song, a photograph, a text message, or even your favorite game. The computer converts all of them into long sequences of zeros and ones. To us, they look completely different, but to the computer, they're all just patterns of binary data. And because everything is represented the same way, the computers can store it, process it, and send it using the exact same hardware. By now, you might be wondering, if computers can use symbols, why just stop at 2? Why not use all 10 digits from 0 to 9 instead? The answer comes down to reliability. With just two electrical states, off and on, it's very easy for the hardware to tell them apart. Even if there's a little electrical noise, the computer can still distinguish the two states correctly. But if we try to represent 10 different states, each one would require a very precise voltage level. Tiny fluctuations in electricity could make one state look like another, leading to errors. So instead of making computers more powerful, using 10 symbols would actually make them more complex and less reliable. That's why computers stick to the simplest and most dependable choices, which is 0 and 1. Now that we have come so far, let's put everything together. It all starts with electricity, which can exist in just two states, on and off. Those electrical states are controlled by transistors, tiny electronic switches that represent zeros and ones. By combining millions and billions of these switches, we can create logic gates that can make decisions and perform calculations. And when billions of these logic gates work together, they become the modern computers we use every day. This approach isn't just simple, it's incredibly practical. Using only two states make computers easy to build, fast to operate, highly reliable and resistant to electric noise. So, the next time you hear that computers only understand zeros and ones, remember it's not because they were designed to understand numbers. It's because it is the most reliable way to represent the physical world inside a computer. And that's the reason every modern computer speaks the language of zeros and ones. But this leaves us with one final question. How does a computer actually understand these binary digits? That's where the CPU, Central Processing Unit, comes in. It's the hardware responsibility for turning long sequences of these zeros and ones into meaningful actions. In the next episode, we'll dive deep inside the CPU and explore how it fetches, decodes, and executes instructions billions of times every second. Until then, thanks for watching Systems Explained. I'll see you in the next episode.